Hello, welcome to section 10.5, the ratio and the root test. Shockingly, we will be talking about two new tests for determining if a series converges. We will talk about the ratio test and, you guessed it, the root test. In my opinion, the ratio test is like the best test out there. When in doubt, you can almost always use it, and it's not that hard to perform. I think the integral test is probably the hardest one to perform. So let's talk about these. So far, everything we have done, the integral test, the comparison test, direct and limit comparison test, they require that all the terms of the series be both positive and decreasing. If the terms are not decreasing, then the nth term test for divergence will give that limit is not zero and that our series diverges. So the ratio and root tests are our first attempts at answering what if the terms of the series are not always positive. So to talk about that, we have a theorem that we call the absolute convergence test. And we have seen a theorem similar to this when we were looking at sequences. This says that if the summation of the absolute value of an converges, then the summation of just an must also converge. And we'll see examples of when the converse isn't true. We can have a series that converges, the summation of an converges, but then the summation of the absolute value of an diverges. So it only goes in this direction. Absolute value implies normal function. So we kind of get something stronger than convergence. We get this, well, not only does an converge, but the absolute value of an converges. The summation of it does. Which leads us to a definition. A series, the summation of an, converges absolutely if the summation of the absolute value of an converges. Thus, by the absolute convergence test, absolutely convergent series also are convergent. If the summation of an converges, but the summation of the absolute value of an diverges, then we call this the series conditionally convergent. So really what we have is we have a series converges really strongly, converges absolutely, and a series converges weakly, conditionally convergent. You can think of these as tiers. So an example, let's see an example. Is the series the summation of -1 to the n plus 1 divided by n squared absolutely convergent? So notice this series does not have all positive terms because of this -1 to the n plus 1. This -1 to the n plus 1 is going to make it oscillate between positive and negative. So to answer if it converges absolutely, we just have to ask, does the summation of the absolute value of -1 to the n plus 1 over n squared does this converge? But this is the summation of 1 over n squared. The absolute value is going to strip away this negative 1 to the n plus 1. So does this converge? And the answer is yes. This is a p-series. That's not how you spell this. Oh, this is a p-series. So, is the series absolutely convergent? The answer is yes. Let's actually write that out. So what we're going to do now is we're going to try to determine tests to decide if a series not only converges, but does it converge absolutely? And if not, then does it converge conditionally? So recall the geometric series. The ratio test is going to be similar to the geometric series. So in a geometric series, if the absolute value of r is less than 1, then the series converges. So the question is, what is r? R we define to be the common ratio, which was the ratio of 2 consecutive terms. Well, we can extend the geometric series test to all series, not just series that are geometric, by, instead of looking at the ratio of 2 consecutive terms and that being constant, so instead of requiring that ratio be constant, we instead look at the end behavior of that ratio. Because at the end of the day, all we care about with series is how does it behave at the tail. Okay, so that leads us to the ratio test. Let the summation of an be any series. So we're not requiring the terms to be increasing, decreasing, positive, negative, nothing. And suppose that the limit, as n goes to infinity, of the absolute value of the ratio we were talking about, an plus 1 over an, suppose that this limit is L. Then we have 3 parts to the ratio test. 1, if L is less than 1, the summation of an converges absolutely. Two, if L is greater than 1, then the summation of an diverges. And 3, if L equals 1, then the test is inconclusive. So similar to the nth term test for divergence, the ratio test could just fail. Okay, so let's see an example of this. So example, does the series summation from n equals 0 to infinity of 2 to the n plus 5 over 3 to the n, does this converge? So first off, I'm going to just immediately say, yes, it does. So we have two ways of doing this. The first way I'm just going to talk through. The second way I'll actually do. The first way does not use the ratio test. We can break up this sum over this addition, and then we'd have 2 to the n over 3 to the n. This series will converge because it's a geometric series with r equaling 2/3. And then we would also have 5 over 3 to the n. Pull out the 5, and then you'd have a geometric series with r equaling 1/3. You're adding two convergent series, so it must converge. But since we know that it converges, let's see that we get that using the ratio test. So we use the ratio test. So we have the limit as n goes to infinity of the absolute value of the n plus first term, an plus 1, divided by the nth term, an, which is the limit as n goes to infinity of 2 to the n plus 1 plus 5, divided by 3 to the n plus 1, times the reciprocal of an, which would be 3 to the n over 2 to the n plus 5. I'm doing this, it's just easier to write it as multiplication than having nested fractions. So now we start reducing. The 3 to the n is going to cancel with part of the 3 to the n plus 1, and we'll just be left with a 3. So that would be 1/3 times the limit as n goes to infinity of the absolute value of 2 to the n plus 1 plus 5 divided by 2 to the n plus 5. This is 1/3 times the limit as n goes to infinity. Divide both the numerator and the denominator by 2 to the n, and you get the absolute value of 2 plus 5 over 2 to the n, divided by 1 plus 5 over 2 to the n. Taking this limit, these 5 over 2 to the n's will go to 0. So you just get 2/3. 2/3 is less than 1. So the ratio test says that the series converges absolutely. And honestly, absolute convergence means nothing here because these terms are always positive. But it's still nice. We get to add another word. So next example. Does the summation of 2n factorial divided by n factorial squared converge? So this is where you really see the power of the ratio test. No other test you could use on this. And this is just a complicated series. You have factorials. We don't know how to take the derivative, the integral of the factorials. So it's just, this is a complicated series. So we use the ratio test. So we have the limit as n goes to infinity of the absolute value of n plus 1 divided by an. And that is the limit as n goes to infinity of the absolute value of 2n plus 2 factorial divided by n plus 1 factorial squared times the reciprocal, n factorial squared divided by 2n factorial. So now we start to simplify this. And what you're about to see is the standard way that you're going to try to simplify factorials, especially when using the ratio test. So first off, group the like terms. we have 2n plus 2 factorial divided by 2n factorial. And then we have n factorial squared, which I'll write as n factorial, divided by n plus 1 factorial times n plus 1 factorial. Start to break up what these factorials mean. So 2n plus 2 factorial means that you take 2n plus 2, multiply that to 2n plus 1, multiply that to 2n, and times 2n minus 1, 2n minus 2, all the way down to 1. But that 2n times 2n minus 1, 2n minus 2, all the way down to 1 is exactly the definition of 2n minus 1 factorial. Or sorry, just 2n factorial. And then divided by 2n factorial. So what we did was we peeled off the first two terms of the factorial so that we got the same thing as the denominator. And we'll do the same thing on the second fraction. We have n factorial, n plus 1 factorial, peel off that n plus 1, and you're left with an n factorial. And then do that again. And then all the factorials cancel. 2n factorial cancels with 2n factorial, and both n factorials cancel with n factorials. So we now have the limit as n goes to infinity of the absolute value of 2n plus 2 divided by factor out the 2, then you get n plus 1 times 2n plus 1 divided by n plus 1 times n plus 1. We can cancel a little bit more. So you get the limit as n goes to infinity of the absolute value of 4n plus 2 divided by n plus 1, which is 4. 4 is greater than 1, so the ratio test says that this series diverges. But this method that you see here, this whole let's peel off terms of the factorial until we get the common factorial so they can cancel, that is how you normally deal with factorials. In general, the ratio test is super useful if the series has factorials. If it has factorials, you should just immediately think ratio test. So, last example for the ratio test. Does the summation of n factorial divided by 2 to the n converge? So I'll let you do this, pause the video, try it, and when you're done, unpause it so that you can see if you got it correct. Okay, we're going to use the ratio test because that's the only test we've been using so far. So we have the limit as n goes to infinity of the absolute value of n plus 1 factorial divided by 2 to the n plus 1 times 2 to the n divided by n factorial. Group the like terms. That is n plus 1 factorial divided by n factorial times 2 to the n over 2 to the n plus 1. Peel off the terms needed in the factorial. So you get n plus 1 times n factorial divided by n factorial. And then go ahead and reduce the exponents. So that would just be 1/2. So this is 1/2 limit as n goes to infinity of the absolute value of n plus 1, which is just infinity. This is not less than 1, so this series diverges. How else could we have seen this? as I said, the n factorials are going to grow larger than almost anything else we see, including 2 to the n. So if you did the nth term test for divergence, you would see that this limit as n goes to infinity does not equal 0. So therefore it diverges. So that's why you should always do the nth term test for divergence first. It would have saved you some time and some work. So we talked about the ratio test. Let's go ahead and talk about the root test. The root test is very similar to the ratio test. Let the summation of an be any series, and suppose that the limit as n goes to infinity, instead of taking the ratio of 2 consecutive terms, the root test takes the nth root of the general term in absolute value. So suppose that this limit is L. But then the outcome is the same. Then 1, if L is less than 1, then the summation of an converges absolutely. Two, if L is greater than 1, then the summation of an diverges. And 3, if L equals 1, then the test is inconclusive. So same outcome as the ratio test. You're looking at what this limit is. Is it less than 1? Is it greater than 1? Or is it equal to 1? But where we're getting this limit is just different. We're taking the nth root instead of taking the ratio. So example, does the summation of n squared divided by 2 to the n, does this converge? Solution, we use the root test. So why would we use the root test? Because we have this n in the exponent. You could also use the ratio test in this case. But if you see things with n in the exponent and no factorials, the root test might be easier. So the root test says the limit as n goes to infinity of the nth root of the absolute value of an, which is the limit as n goes to infinity of the nth root of the absolute value of n squared divided by 2 to the n. This is the limit as n goes to infinity. In this case, n squared over 2 to the n is positive, so we can get rid of the absolute value. So that would be the nth root of n squared divided by the nth root of 2 to the n. This is the limit as n goes to infinity of the numerator we can rewrite as the nth root of n quantity squared, and the denominator just becomes 2. Take this limit and we get 1 squared divided by 2, which is 1/2, which is less than 1. I'm going to talk about this limit just in 1 second. So to finish the problem, the series converges absolutely. So talking about this limit, recall that the limit as n goes to infinity of the nth root of n, we can rewrite this in the most obvious way you would ever think of. This is e to the natural log of the nth root of n. Super obvious, I know. This is the limit as n goes to infinity of, you can pull out this exponent, the nth root, since it is inside of a logarithm. So that would be natural log of n divided by n. Since exponential functions are continuous, we can bring the limit inside of the exponential function. Then, using L'Hopital's rule, this is e to the limit as n goes to infinity of 1 over n divided by 1, which is e to the 0, which equals 1. You may use this fact freely. You do not have to rederive this limit every single time. But when using the root test, you'll probably get the nth root of n multiple times. So you can just immediately know that that limit is 1. Last comment, I already said it, I'm just going to write it down. The root test is super useful for series that have a to the n. As you saw in this example, the 2 to the n was just reduced to a 2, a 1/2, which makes the root test very convenient here. But note, you probably don't want to use this, probably. You probably don't want to use the root test if it has a factorial. If it has a factorial, you should use the ratio test.